right. So, in this particular lecture, that is lecture 2, we are going to discuss the stagecoach problem, how to solve stagecoach problems, which is a shortest distance problem by making use of dynamic programming, right. So, that is going to be our topic for this particular lecture. Now, again let us start with Bellman's principle of optimality. It basically states an optimal policy has the property that whatever the initial state and the initial decisions are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decisions. Is it all right? So, that is Bellman's principle of optimality, and we will come back to this once again. The stagecoach problem is essentially let us say a stagecoach is moving from a city A to a city J, is all right. The stagecoach has to move through number of cities, and initially to a set of cities B, C, D, from where to another set of cities E, F, G, to another set of cities H and I, and finally to J. Obviously, it can take a given path. For example, it can go from A to B to E to H to J, or it can move to a totally different path, say A to D to F to I to J. So, you can see that the stagecoach need not go to all the cities. It can choose a particular set of cities from the source to the destination, and in order to fulfill some objective function, right. Maybe the shortest path, maybe the minimum cost, is it okay, maybe maximize profit, and things of that sort. So, if you recall in our previous class, what exactly I said is that assuming we have somehow come to a given city G. So, having come to G, irrespective of how we have come to G, we must now optimally complete our journey from G to J in the optimal manner, right. So, if we find the optimal path from G to J, is it all right, that optimal path will help us in finding the total optimal path from A to J by combining. So, you see, supposing we start our journey from G itself, then how about what is the optimal path from I to J? You can see very clearly the optimal path from I to J is 4 only, because there is no other path. Obviously, you can go from I to E, go back and then come to H and then J, but then those paths will be much longer. So, I to J, that is the optimal distance from I, city I to city J. So, if we know that in order to go to J, either you have to come to I or to H, and optimal distance from I to J is 4 and H to J is 3. So, if we know these facts, can we find out what is the optimal distance from G to J? Look here, G to H, the least distance is 3, and G to I, the least distance is 3 again, and I to J, the optimal path is 4. So, what is the optimal path from G to J? Is it through I or is it through H? You can see that G to J through I is 7 and through H is 6, right. So, therefore, the G to J the optimal path is really 6, right. So, this is how, as I said in my previous lecture, we can create a dynamic programming methodology through which we can find the optimal solution. But before even that, let us see how this how this optimal path can be actually the problem, how the stagecoach problem has originally, I mean how it originated. The story goes like this: somewhere around 1900s, a fortune seeker in Missouri travels to California by stagecoach to join the gold rush through unsettled country of serious danger. Is all right. So, although his starting point and destinations were fixed, he had a lot of choice in his route of travel. So, being prudent to consider safety, he found out that the safest route should be the one with the cheapest total life insurance policy. Because in those days, as the stagecoaches used to travel through these unsettled countries of serious danger, they used to go for life insurance. And these life insurance companies used to ask for certain premium depending on what is the risk in that given path, right. And it is possible for a person to find out those life insurance policy premiums. Is it all right? So, if you really count all these policy premiums to move from a given city to another city, let us say from A to B, A to C, A to D, etc. So, you know all those policy premiums. Instead of the distances, if you look at those policy premiums, because these policy premiums apart from the stagecoach travel costs, these policy premiums will actually determine because stagecoach travel would depend on, let us say, the number of days, and we know the number of days, assuming from a given city to the next set of cities the number of days are more or less the same. So, it is the insurance policy premiums which are going to decide the total cost of the path, or maybe you can even say the safest path will be that where the cost of the policy is minimum. Not only you see you pay less, but also your risk is the least. So, that is how the stagecoach problem was originally formulated, and this model therefore would look something like this, that from A to B, let us say cost is 2, A to C cost is 4, A to D cost is 3, and like that, then what is the path from A to J that one should take, so that we get the least possible cost, right. Sometimes we can actually make a matrix of this form, very easily we can find out the costs, let us say A to B is 2, A to C is 4, and in these matrices they can be called as distance matrices. The distance matrices gives us the cost figures in a very summarized way. So, what we need to find out? We need to find out the shortest path. So, what should we do now if we have to solve this problem from dynamic programming point of view? What are the different things that we should fix up right in the beginning? Please recall our previous lecture. Can you tell me what are the things that we should fix now? Number 1 is the stages, different stages, right. Number 2, the different states, right. Number 3, the decisions that we should make at every stage. Is it all right? And fourth, the recursive relationship which connects a given stage to the next stage, right. So, these are the things that we should fix up to solve this problem with dynamic programming. So, what are some stages and states? Is it okay? So, as you can understand very clearly that every leg of the stagecoach run can be called a stage. Is it all right? So, from the first set of cities, let us say A, to the next set of cities you move, this is called stage 1. So, in stage 1 you actually move from A to either B or C or D. So, this is stage 1. In stage 2 you move set of cities B, C, D to set of cities E, F, G. Is it all right? In stage 3 you move from E, F, G to H, I, any one of them. And in the final stage you move from H, I to J. If you are in H, go to J, if you are in I, you go to J. So, these are the 4 stages. And what are the states? You see, at every possible stage, after the conclusion of the stage you reach a state. So, there is only one state to begin with and there is only one state to end with. But after the conclusion of stage 1, you may be in one of the possible states, that is B, C or D. And after the conclusion of state 2, you can be in E or F or G, and at the conclusion of stage 3, you can be in H or I. Is it all right? So, these are the stages and states. Is it all right? So, I hope it is clear. The stages are every leg of the stagecoach run. States are at conclusion of the stage where what are the possible different states where one can be in, right. Now, the decision variables. The decisions in the shortest path problem are x n, which can be called as the immediate destination on stage n, that is the nth run between cities. So, supposing hence a route will be A to x 1 to x 2 to x 3 to x 4 to j. So, to understand this, let us draw this diagram here. So, this is the A, then B, C, D and E, F, G, then H, I and then J. Is it all right? So, x 1 could be either B or C or D. X 2 could be E or F or G. X 3 could be H or I, all right, and obviously x 4 is J. So, there is no x 4 separately because there is, that is all, we do not have any other. So, we start with A and then in between there are B or C or D and then E or F or G and H or I and then finally J, right. So, there is no separate J here, the x 4 itself is J. Is it all right? So, that is all that we have from A to B or C or D, that is the destination city, then E or F or G, then H or I and then J, right. So, that after the completion of all the 4 stages, I find the x 1, x 2, x 3 and x 4 and then I find the final route which will give us the shortest cost. Hope it is clear that we decide the stages, we decide the states and we decide the decision variables, and with the help of the decision variables we can find the optimal path, all right. So, that is how it goes. So, now that we know this, let us see the recursive relationship. Now, this is very important. Before even we discuss this, let us look at another very interesting thing. You see, in this particular diagram, what we find out, if we move from one state to the other, we find out that as we go from in the stage 4, as we go in the stage 4, suppose this is our consideration, this is our consideration in stage 4. You see, this is our consideration in stage 4. So, we find certain optimal decisions. What are those optimal decisions? That if we start from H, then supposing we can write f star H, then it will be 3, and the optimal decision from I will be f star 3. So, this will be 4. So, f star H is 3 and f star I equal to 4. So, what are they? They are my stage 4 optimal decisions. So, you see, this is our consideration in stage 4, but then what is our consideration in stage 3? Our stage 3 consideration are these. Please do not forget this, that although we are really concerned about these parts. So, you see, when at stage 3 our consideration also includes stage 4 decisions, but then out of that only this much we focus, and these stage 4 optimal decisions we actually make use of. So, look here, what is the optimal path? Suppose we are in stage 3, what is our optimal path from G to J, right? Is it through I or is it through H? We only have to do, we do not have to really compare all the way from G to J, through H, through I, not required. I only look at G to H is 3 and H optimal distance is 3, is it all right? So, the optimal, so what is f star G? F star G is minimum of 3 plus f star H, comma 3 plus f star I. Look here, we make use of these f star H and f star I, which are stage 4 optimal decisions in stage 3. So, the optimal path from G to J can be obtained, by making use of the f star H and f star I values. Is it all right? And since f star H is 3, so this value comes out to be 6. So, these f star G values, I can find out and I can keep it as an optimal decision for stage 3, which will make use in the stage 2, where considerations will be all these. And when the entire thing is considered at stage 1, then we find the overall optimal decision from A to J. Is all right? So, this is the kind of philosophy that we usually follow for dynamic programming, right, and how we go about it, that is all we are going to see. So, having said that, let us see how we can forward or move further. So, exactly same thing is written here in a slightly different language, that if we have the optimal decision that we know, which is f star n plus 1, suppose n equal to 3, that means we want to find out the optimal decision of f n star s, then it is making use of the f n star n plus 1, the next higher stage, what is the optimal decision. So, optimal decision is here. So, this is our optimal decision at the next higher stage, right, and the distance from the current city, suppose let's draw that once again. So, here is here is E f g, and here is H and I, right. So, there are paths from all these cities. Now, we know F star H and we know F star I. So, you see F star H and F star I are actually these values, right. So, F star n plus 1 x n, which is the next stage optimal value. What we find out is the distance from S to x n, that means G to J H, x n is H or I. So, G to H or G to I, then we add this portion and then find out of H and out of I from G, which one comes out to be optimal. So, this will become our F star n s. Is it all right? So, exactly that thing is happening, that is F n s x n, distance of the best overall policy for the remaining stages given a run from state S ready to start stage n with immediate destination x n. Is it all right? So, d s x n is the distance from state S to immediate destination x n. F star n plus 1 x n is the optimal distance at the previous stage with x n, and F star n s is the corresponding minimum value of F n s x n. All right. So, like this, by making use of the next stage optimal decision. So, this is our next stage optimal decision, making use of next stage optimal decision and the distance from a given point S, state S to the destination x n, I can find out the value for this F n s x n, right. And if I have many such values, because depending on the various combination, the minimum amongst them of with regard to x n will give the new optimal value at the next stage. So, that is going to be our recursive relationship, and this recursive relationship we can make use of in our computations. So, let us see how we compute, right. How we compute, let us see that. So, that is our stage 4 calculations. The stage 4 is very straightforward. The stage 4 calculations, all we have to do is find out the optimal path from H and I to J, and since this is the last stage, it is very simple. Obviously, from H to J there is only one path and therefore, the optimal is 3, and I to J there is only one path. So, optimal is 4. So, the destination city is only one. So, x 3 equal to J. From H to I the distances are 3 and 4. So, F 3 star S will be 3, that means F 3 star H, these are S actually, right. So, if you take the pen, this is S, right. So, S is either H or I, and F 3 star S is 3 or 4, and x 3 star is J. Is it all right? That is the destination city. So, this is our stage 4 calculation, which is very straightforward and we can obtain it very easily. So, having obtained this, next see that how we go to our next stage, that is stage 3. Now, while we make our stage 3 computations, we must remember that we have calculated our stage 4 optimal decisions, where if S is H or I, then F star 4 S is 3, F star 4 S for I is 4, and x 4 star was J. So, we shall make use of these decisions in our recursive relationship. So, what is those recursive relationship? Now, from E we can go either to H or to I. Is it all right? Similarly, from F to H or G to H, F to I, G to I. So, all these computations we have to do, right, but please understand the good thing that is happening, we are making calculations only between a given stage of cities to another state of cities, set of cities in the stage only, right. We do not have to go beyond, that is the advantage that we have. So, we know F star H, we know f star I, we are making use of them. Say f star h is 3 and f star I is 4 and d from d e to h is 1. So, it is 1 plus 3 4 and here e to I is 4. So, e to I is 4. So, 4 plus 4 8, right. Now, 4 and 8, what is the lower value? The lower value is 4. So, obviously, the f star E will become 4 and destination will be H. Why destination has become H? Because that H part has come out to be the minimum. All right. So, similar calculation for f, you will find the lower value comes with I. So, obviously, x 3 star will be I, that means we have to go through I and that value is 7, is all right. And when it comes to G, it should be d g h plus f star 4 and that comes to 6. So, this will become 6 and these are become H. So, we have now obtained the optimal decisions for the stage 3, right. So, having found the optimal decisions for stage 3, again look here, we noted down the stage 3 optimal decisions and which are also indicated in this plot. Now, we have to see from the stage BCD to EFG. When we see from BCD to EFG calculations, again we make use of these optimal values which are 4, 7 and 6. So, 4, 7 and 6, 4, 7 and 6, 4, 7 and 6, adding the respective distances. So, only distances are to be covered are between these set of cities BCD to EFG, you do not have to see any further. So, you see what are we really advantage we got by making use of dynamic programming. We can only see the distances between a set of cities to the next set of cities, which are finite. We really do not have to see combinations which are before or which are after, because we already have the optimal value from the next set of stages and those optimal values we are making use of through the recursive relationship. So, this is where the real advantage comes in and those advantages can be made use of. So, we see that from B the calculations that both B to E and B to F they are minimum. So, the destination optimal is E and F both and the value is 11. Similarly, for D the value is 8 and the destination cities are E and F. Those are stage 2 calculations. Coming to the stage 1 calculation, there is only one starting city, right, and those optimals BCD has been made use of, right. So, F2 star B is 11, F2 star C is 7 and F2 star D is 8. So, only 3 distances are there 2, 4 and 3. So, when you made use of them you get 13, 11 and 11 and we know that 11 is the minimum. So, 11 is the optimal distance and destination cities are both C and D, is it okay. So, this is our stage 1 calculations by making use of the recursive formula. Now, here we have listed all the optimal decisions stage 4, stage 3, stage 2, stage 1. So, from A we find that the there is a mistake here, let us correct it. So, this is not 29, this is really 11, right. So, the previous distance. So, previous distance it was 11 C and D. So, yeah. So, I do not know why it has been mistakes, anyhow this is corrected. So, it is 11 and this is C and D, right. So, the optimal is 11 and C and D, right. So, this is 11 and C and D, they are optimal. So, now you can combine that what is if you go to C, then from A the distance is C and from C it is E, from E it is H, from H, it is J. So, A, C, E, H, J, this is 1. If you go to D, then A to D, D to E or F, if you go to E, then H, then J. Now, if you go A to D, then from D to F, and from F to I, from I to J. So, A to D to F to I to J, and the distance are all 11. Is it all right? So, those are our optimal distances, that A to C to E to H to J, 4 plus 3 7 plus 8 plus 3 11. So, this is one optimal. Then other one is A to D to F to H to J, this is also 11, and A to D to F to I to J. So, 3, 4, 7, 11. So, there are 3 optimal solutions which can be found out, and all of them are really optimal solutions, right. So, this is how we solve the example stagecoach problem, and we shall take up more problems in the subsequent lectures, right. So, thank you very much.